All right, so again, this was I was in the last video we were talking about this Shapley using the globular clusters and basically mapping their positions. Just figured out that the center of the galaxy was in the direction of Sagittarius, because that's where all the globular clusters seem to be orbiting that common spot, which is the direction of the center of our galaxy, it turns out. And he didn't get, like I said, he didn't get the measurement correct because of, he didn't think about, and nobody did at the time, the reddening due to gas and dust. Anyhow, with modern techniques, we're able to measure this, to measure the center of the galaxy much more accurately, and we get a better picture of where we are in our spiral galaxy, the Milky Way. Let's talk just a little bit about this. This is important because a lot of these women that were, as they say, hired as computers. I mean, this was actually done well into the 1950s, and not just by Harvard University. I mean, the ones I'm about to talk about were mostly at Harvard, but this was a common practice, and a lot of these women did not get the credit, certainly during their lifetimes, that they certainly deserved. They absolutely deserved. So I think it's nice that a lot of these books now, a lot of the astronomy textbooks now are devoting some time to this, and I want to talk about this as well. All right, so let's see. So let's take a look. Remember Annie Jump Cannon, who let's see. Can we see? Sure, she's in this one. So this is I don't. I think that if you read the electronic text, it'll actually show which one she is. I can't remember. Anyhow, she, remember, is the one that came up with the spectral classification system using temperature, right? So that was a huge contribution, which of course helped. The people who came up with the HR diagram, Hertzsprung and Russell, who were both guys, didn't give any of these women any credit for doing any of that. That was just kind of overlooked back then, and that's tragic that was overlooked. And then, of course, Henrietta Leavitt was one of these so-called computers working for Harvard, and she's the one who came up with this period luminosity relationship that allows us to extend our distance into our ability to measure distances to stars further out into the universe than we had ever done before. All right, so this is, and if you read the e-text, there's a lot more information about these ladies who just were pioneers in the field of astronomy, certainly in the early days of the 20th century. All right, so this is basically the picture that we get, with all the work that has been going on. So this is, of course, an artist's rendition, but this is the basic idea. If we were looking at the galaxy from the side, there are three basic parts of the galaxy that I want to talk about, okay? So the first part is the center, the middle of the galaxy, and that's called the galactic bulge, or sometimes it's just commonly called the bulge. All right, so spiral galaxies always have this, remember, right now we're just talking about our galaxy, but there are other spirals. In fact, the Andromeda galaxy is the closest one to us. Anyhow, So the galactic bulge, that's the nucleus, if you will, of the galaxy. Then there are the spiral arms, also known as the disk of the galaxy. That's where this relatively flat part. It's not entirely flat, but it's much thinner than the galactic bulge, and then so that's where we find our sun and lots of star formation, new star formation taking place, and then surrounding the entire galaxy. All right, so so surrounding the entire galaxy is what's called the halo, or the galactic halo, just halo for short. So just like we'll generally call the spiral arms the disk of the galaxy, and then the galactic bulge the bulge of the galaxy, or the nucleus of the galaxy, and then the halo. Usually you just refer to it as the halo or the galactic halo. It's the same thing. And the galactic halo, of course, is where the globular clusters exist. And there turns out to be something else there as well. Something that was a great surprise to us as astronomers. It was there's this stuff called dark matter that exists in the galactic halo. We'll get to that in a little bit, but that was a complete surprise. And it turns out there's more dark matter than there are stars in the galaxy. So we'll get to that too. So the three basic parts, the halo, where you so this is let's go over some of the properties of these three main parts of the galaxy. Right. So the halo, you're going to find the globular clusters that are extremely old. These things are at least 10 billion years old. Some of them are 12 billion years old. And this is where we find the oldest stars. And the other thing about this is, out there in the halo, in the globular clusters and in the halo, you don't find any gas and dust. So there's no new star formation. That's actually really important to remember that. In the halo, you do not see new star formation. Remember, that's if you go back to the chapter on neutron stars, right? The chapter right before this, chapter 22, when we first started talking about neutron stars, we found the very first milli-neutron stars, right? Where their period was in milliseconds, was in the galactic. In the globular clusters, and that was really confusing because we knew that there's no new stars forming, and so a neutron star that's a pulsar that's rotating that fast should have slowed down over the course of 10 billion years, and should not be still rotating around that fast. And of course, we figured out that those things had been sped up by receiving material, hydrogen from other nearby stars, and therefore causing the star causing a torque that sped up the rotation of these pulsars. All right, so the globular cluster is very old, no gas and dust. The galactic disk. That's where the spiral arms are. That's where the youngest stars are, like our sun. Our sun, even though it's 4.5 billion years old, it's still considered a relatively young star. Remember, it's kind of, you probably think of it more of a middle-aged star. It's kind of in the middle of its life cycle. It still has another 5 billion years to go where it's converting hydrogen into helium. And we also find nebula, large clouds of gas and dust, and of course star-forming regions like the Orion Nebula, right? So there's plenty of gas and dust to form new stars, and remember that the new stars form from partly from material the old dead stars that have blown up, well, some of them have blown up. Some of them are just the planetary nebula, the lower mass stars. The planetary nebula is expanding out into space and enriches the interstellar medium with heavier and heavier metals. And so when you have a star like the Sun forming, there are a great you get most of the elements on the periodic table because the stars have had enough time for stellar evolution to have taken place. So stellar evolution is the sense that not like biological evolution, but more of that when new stars are formed, they have the metals already in them, and then of course when they die, they're going to create even more metals, and then so the next generation of stars will have even a higher percentage of metal content. And then of course surrounding the galactic center is this thing called the galactic bulge. There's actually a mixture of older stars and younger stars in the bulge itself. So that's this part of the galaxy. It's much more dense in here than out here in the spiral arms, where we kind of live in. If you think of it as a very heavily populated city. We're way out here in the suburbs where the spiral arms are. All right, so it's much more peaceful. There's more space. There's more room. That kind of thing. All right, so that's the three main parts. Don't forget that. And of course, when we try to look into the center of our galaxy towards the galactic bulge, we are obscured, right? The visible light can't pass through because there's so much gas and dust. The photons of visible light just can't get through. Remember, it always has to do with the physical size of the wavelength of light. So if you change the wavelength, of course, if you change the wavelength, you're changing the type of light. So you get more towards, like infrared or microwave or even radio. Radio waves can pass through, and so in that sense, we can, and I'm using air quotes here, see the center of the galaxy with other forms of electromagnetic radiation. So let's see, stellar orbits in the disk move in the plane in the same direction. Orbits in the halo and the bulge are much more random. So you can see. In the part that we're in, the disk or the spiral arms, everything is rotating along in the same overall direction. That's a little bit. It's not like it's rotating as a solid object. I want everybody to understand that it's not at all a solid object. In fact, we think that the spiral arms get concentrated in certain areas and then expand further in other areas. But the other thing of it is the halo and where the nuclear bulge is, the stars are moving in all sorts of directions, right? Some of them are moving this way, some are moving clockwise, counterclockwise, towards the side. I mean, they're doing all sorts of crazy things. But the spiral is they're all, oops, I'm going in the wrong direction. They're all moving in the same direction. So the sun and Alpha Centauri and all the stars that you can see in the night sky are all moving in the same direction. All right, so here are some ideas about the formation of the Milky Way. So we've got to be able to account for all the different properties, and we try. This is an ongoing area of research, is to try to explain the things that we see. The first thing is that the disk of the galaxy is really flattened, right? And then the halo, of course, is highly spherical. And then the bulge is kind of like football shaped. It's not. Let me go back to the picture. It does not do it justice. This looks spherical, but it's more more like a football. It's wider.